All right. Hello, my name is Jesus,
My name is Yeamlak.
and today we have a special video with,
I'm Kofi.
and today we're going to teach rational equations. All right, let's start off. So, first I'm going to teach some basics about rational equations. So, what is a rational equation? Here we have a parent function of a rational equation, which is 1 over x, and we can see some attributes already starting off. So, asymptotes. We have a horizontal and a vertical asymptote, this being the horizontal and this being the vertical. Horizontal asymptotes are expressed by y equals a number, and vertical asymptotes are expressed by x equals a number. You can see this x equals 0, this y equals 0. Intercepts. So in this graph, we don't have any y or x intercepts, but they're also points. So an x intercept could be 1 over x or over 0, and a y intercept could be 0 and 1. Holes. Holes are removable discontinuities that basically cancel out. We'll talk this more about later. So let's have x minus 3 and x plus 2. If we have another x minus 3 here, cancel that out. That means that the graph will not exist at x minus 3. So it won't exist at positive 3. So this will look like a little open dot. All right. So rational functions do not only look like that, they can also look like something crazy like this, where you have a hole. All right, next topic.
Up next, we got vertical asymptotes. So what are vertical asymptotes? They're lines that a graph approaches but never touches. So for vertical asymptote, the parent function of a rational function is represented by f of x equals 1 over x. Basically, that's the line this. To find the vertical asymptote of a rational function, he said the denominator equal to 0. So, to find the vertical asymptote of this example, he said the denominator equal to 0. What do I mean? He said x minus 4 equals 0, x plus 2 equals 0. X minus 4 gives us x equals positive 4. X plus 2 gives us x equals negative 2, as it is shown on the graph here. Why are vertical asymptotes important? They tell us where a graph cannot exist. Vertical asymptotes help us determine that whether graphs can be plotted or not be plotted. The reason for dividing by 0 is any number divided by 0 is undefined. And an undefined function cannot be graphed or plotted on a graph.
Alright, so now we're dealing with horizontal asymptotes. Horizontal asymptotes are basically horizontal lines specifically, in which the graph seems to approach it, but it never actually touches that graph. So we're going to deal with one of the scenarios regarding the horizontal asymptotes. There's a total of 3 scenarios: proper, improper, and neither. So when we're dealing with a neither, it means that, for example, when we're dealing with neither, what that basically infers is that the maximum power for one specific term on the numerator and the denominator are equal. So basically what that means is a rational function is defined as f of x equals a of x over b of x. And a of x and b of x are separate terms. And for the highest power for one specific term found in the a of x function, and the one found in b of x functions are the same. So for example, if you have x squared plus 3 here over x squared plus 3 over x squared plus 3x, for instance, but this would mean, since the highest power over here is 2 and both of them are equal, then we're dealing with a neither scenario. And when we're dealing with neither, the primary rule regarding the neither horizontal asymptotes is to look at the coefficients of the functions. So over here, after distributing, you would know that there would be no coefficient on the x squared term. So the coefficient right here would be 1, and the coefficient right here would be 1. And we take the ratio of the coefficients, which is just basically 1 over 1, which is 1. And at line 1 is your horizontal asymptote, as shown right here.
Now, coming up is one of the more challenging rational functions, being a slant asymptote. That is when it is improper. So that is when you have your numerator to a higher degree than your denominator. To solve for the slant asymptote, all you have to do is divide the numerator, with the denominator. So let's just follow this out really quickly. You have x, it's x squared. You have 2x plus 2x. You have x, 1 plus 1, 1 times 1. So you have this. This will be your top equation divided by 1 over 2. We can use syntactic division to find this equation here. Let's start with our coefficients. This is 1, this is 2, and finally this is 1. And let's find a root. To find the root, you simply set your denominator equal to 0. So x equals to -2. Our root will be -2. So drop down the first number. -2 times 1 is -2 equals 0. 0 times -2, 0, drop down to 1. That means that our equation will be y equals 1x plus 0x, or just simply x squared, with this being the remainder. As you can see, it's that graph plotted in here. Rise over 1, 1. It's just y equals x. Quick summary: to find the slant asymptote, you divide the numerator by the denominator using long division or syntactic division. Now, let's try a real problem.
So right here we have the slant asymptote problem. So when dealing with slant asymptotes, again, you have to divide the top function over the bottom function. And when doing this, we could use two separate methods. We could use synthetic division, or we could use the polynomial division method. So over here, since there is a cube and a square, I would more likely use the polynomial division method, because it would be way easier than actually doing the synthetic division. Right, so we have x cubed, but right here you can see that it skips the square, so there is no x squared term. So we assume that there's a 0x squared term right over there. So 0 times x squared is still 0. So it doesn't really exist, but the only reason why it exists is because it's necessary when you're dealing with a polynomial division. So we have x squared plus 2x minus 5. And right here you would have x squared minus 9x. Alright, so now we would find the perfect term right here would be x. So now x times x squared, and we would have x times x squared minus x times 9x. So we would have x cubed minus 9x squared. And we're subtracting here. Unlike synthetic division, we're actually subtracting. So these two cancel. and you'd be left with 0 minus 9, which is just 9x squared. And then we bring down the plus 2x right here. And now we try to find the best number to use here, and it would be 9, because again we're trying to remove the highest degree in this section, or in the bottom section. So that would be, if we put 9 there, then 9 times this function would be 9x squared minus 81x. And when you subtract this, these two cancel, and you would be left with 2 minus 81x. And 2x minus 81x would give you 83x, and then that would be it. So now it becomes minus 5. So there is no other term that you can use. And now we have our x plus 9 term, which is our quotient, and 83x minus 5, which is our remainder. And the reason why we can continue with the synthetic division is because the power here is 1 and the power here is 2. So we can't have any other physical values unless we divide by x, and which we don't do. So that would be our slant asymptote. Again, slant asymptote deals with the division of polynomials, and make sure to be careful when you're dividing them.
Up next, we got x-intercepts. So basically, an x-intercept is where y equals 0. That's an x-intercept, like, basically. So anytime y equals 0, like at this point, y equals 0, y equals 0. That is an x-intercept. So to find the x-intercept of a rational function, like the example we have here, you equate the numerator to 0. Unlike the vertical asymptotes where you equate the denominator to 0, for x-intercepts you equate the numerator to 0. So in the numerator we have x. So about there, see, we got x plus 1 equals 0, and x minus 7 equals 0. So how do you do this? You do this by adding 7 to this and subtracting 1 from here. Whatever you do to one side, you do to the other side. So you subtract 1 from here, so you add 7 to here, giving us x equals -1 and x equals +7. For these, you got the x-intercept here to be -1, and the x-intercept here to be +7.
Alright, so now that we've talked for x-intercepts, we'll now mention y-intercepts. Y-intercepts are very different from x-intercepts, but they have the same thing. So how do we find a y-intercept? We set the x equal to 0, because for a y-intercept, x has to be equal to 0, and here will be a number. So 0, 0, 0, 0, we're left with 1 times -7 divided by -4 plus 2. So let's simplify. 1 times -7, that's equals to -7 divided by -4 times 2 is -8. These cancel out, so you'll be left with a 7 over 8 equal to 0.875, which will be our y-intercept. 0.875. As you can see here, the exact same number. So to find y-intercepts, just remember, set every x equal to 0, and solve.
Alright, so now another key concept to understand when evaluating or when working with rational functions is holes, or in other terms called removable discontinuities. So basically, holes or removable discontinuities are a point on the graph where there's a literal hole. So assume that place or that position on the graph doesn't exist. That's why we represent it by an open circle right there. It's basically a free spot or a dot of space in which the graph basically skips. So if the graph were to go like this and there's a hole, it's gonna essentially skip it like that. So how do these removable discontinuities or these anomalies occur? So oftentimes you find removable discontinuities when simplifying or when analyzing the rational functions themselves. So for example, if we were to let's say we have this rational function, which is the graph of this, and we can see it has a removable discontinuity. Let's analyze it. Let's factor it out, for instance. So if we were to use, per se, the square method, we would realize that the top would be x squared minus 2x plus 4 over the bottom would be x squared minus 3x minus 2x plus 6. Let's factor this out. So we would have x times x minus 2 2x like that over, let's factor the bottom one also, so we have x times x minus 3 minus 2 times x minus 3. So when we evaluate this, we would see that we have x minus 2 times x minus 2 over x minus 2 times x minus 3. So as you can see, we have two common terms on the top and the bottom. So intuitively, we would cancel them out. But in doing so, we are ignoring the presence of a hole. A hole occurs when a term from the numerator and the denominator can cancel each other out, and that at that specific root, the root of that term would describe to you the x coordinate of the hole. So what I mean by that is you essentially canceled out x minus 2 right there. But let's take that common root, the root that we took, so which is x minus 2 itself, and let's set it equal to 0. So when we find the root, it would be at x equals 2. So basically what this infers is that when x equals 2, the graph just skips a point. So the graph doesn't exist at x equals 2. And holes are completely different from vertical asymptotes because they don't describe a point and they don't describe a line in which the graph appears, but instead a removable discontinuity. And basically the part where the graph disappears. And not all rational functions have holes, but it's essential to keep an eye out for them because they're a key and intuitive part, especially when you're advancing into calculus. So here is another section that you must pay keen attention to because it gives you the step-by-step instructions on how to graph. So you could use this simple mnemonic, have iguanas visit hot gardens. So what that basically means is first you look for holes, removable discontinuities. Find any removable discontinuity on your graph because they might trick you and change this. You might consider them as vertical asymptotes, and that would generally mess up the shape of your graph. So make sure you find your holes find all the holes in your graph. Second, find your intercepts. So finding the x-intercept and the y-intercept, it's key because it allows you, it guides you to where the general direction of the graph will be. Thirdly, you have the vertical asymptote. So the vertical asymptote is also another key thing because you set the denominator equal to 0, and then you solve for the root of that function, and you find your vertical asymptote. And that vertical asymptote is also key because it's one of the most important part of your rational function. You have next you have your horizontal asymptotes / slant asymptotes because remember there are three cases for the horizontal asymptote, and one of them might lead to not having a horizontal asymptote, but instead having a slant asymptote. So make sure you distinguish which is which, and find either your slanted or your horizontal asymptote. And then lastly, you graph. So that's a simple mnemonic that you could use as a step-by-step on your test. So yeah, never forget, happy iguanas visit hot gardens.
Alright, so next topic. In this topic, we covered three special things. They are called the three cases of horizontal asymptotes. So we have, let's change that to white so it's clearly visible. Alright, so we have first, proper. I don't know how to spell. Proper. Then we have improper. And lastly, we have neither. Is that how you spell neither? You sure?
Yeah.
Alright. So these cases will tell you whether if it's y equals 0, y equals a ratio, or y equals a slant asymptote. So for proper, you have, let's say, x squared, and you have x to the power of 3. So for this one, as you can see, your denominator has a greater power than your numerator. This will consist as a proper function, since your denominator is bigger than your numerator. So what that means is that it will always have a horizontal asymptote at y equals 0. So, next up, neither. Neither consists when you have an equal. So when you have x over 2 divided by an x over 2. As you can see, these powers are the same. So what you would do is divide the coefficients. Let's say that there was a 2 here, and let's say that there was a 3 here. What you would do, simply just divide. The horizontal asymptote would be equal to the ratio. So 2 divided by 3. Anything you have, let's say a over b, you have your x squared divided by your x squared, it will always be a over b. Now, the hard one, improper. Improper happens when your numerator is bigger than your denominator. Let's say we have, I'm going to show it differently. Let's say you have x minus 3 divided by x minus 3. A quick and easy way to know if you expand your function to see which actual numerator or denominator has the bigger exponent, you just look at the x's. You count the x's. Here's 1x, here's 2x, so top is 2. This will only happen if they are multiplying together. If they're adding together, let's say for x squared plus 1x, these will not count as 3. You will only look at the leading coefficient, or the one with the highest power. Since they are not multiplying each other, they are adding. These are multiplying. So what that means that if you fold it out, you would get an x over 2 as a leading coefficient, x to the power of 2 as a leading coefficient. As you can see here, this is only 1x. So it would be x to the 1. That's a quick and shortcut. As you can realize that the numerator has a bigger power than the denominator. Those will always have a slant asymptote if there are no holes. And they would be equal to y equals mx plus b, where you have your slope and you have your y-intercept. All right, so hopefully you enjoyed this video. If you have any questions, comment down below. Just remember the mnemonic, happy iguanas visit all gardens. Happy pre-cal or algebra 2, wherever you're at.